the next seminars, I would like to.
Server or our server, we should check. I'm not sure.
Right.
But
we can start.
Okay.
so, Valdelina, are we ready? I'm
Yes.
not sure. Okay.
Yes. Okay. So welcome everybody. I'm very happy to introduce Claudia. She received her PhD from the University of Cambridge, and nowadays she's a professor at the Imperial College at London. She works in many topics, such as particle physics, gravity, and cosmology. For her work, she received several grants and awards. To mention one, in 2020, she became a Simons Investigator in Physics. Today, she's going to tell us about probing gravity and gravitational waves. The title of her talk is Causality in the Sky. Thanks a lot, Claudia, for accepting our invitation, and the word is yours.
Thank you very much. Thank you for this warm welcome. So let me share my screen. Can you see my screen?
Yes.
Okay. Thank you very much. Yeah. So I'll be talking about causality in the sky. You'll see what I mean by that very shortly. But let me start with a brief introduction of what I'm interested in. And saying how amazing work we're doing, both at the interface between cosmology, gravity, gravitational waves, and particle physics, with experiments and observations that are pushing really the frontiers of our knowledge and are in impeccable agreement with our understanding of how gravity, how particle physics, how cosmology should be working in the standard paradigm. But at the core of all of those success, there's always a slightly more negative approach, which is wondering what is uncovering all of the open questions that are at the interface between gravity, cosmology, and particle physics. For instance, the dark energy problem or the related cosmological constant problem, some other naturalness issues, for instance, the hierarchy problem, the presence of dark matter. All of those open questions may be signs that new physics is to be uncovered, and maybe this is a chance, an opportunity for us to dive deeper within the layers of physics. So with that in mind, it'll be nice to see if we can establish some connection between the low energy observable, for me, the standard model of particle physics, even though it can go all the way up to the TeV scale. For me, this is still low energy physics as compared to the scale at which possibly the ultimate completion of gravity or an ultimate completion of everything may come out. So we'll try to understand whether we can establish a contact between high energy physics and the low energy effective field theories that we are observing in our everyday life with our current tools of physics. And ideally, we'll have a unique high energy completion for quantum gravity and for everything, which is completely natural and complete in itself. And from there, we could cascade our way down to a single model for the representation of everything, the universe, particle physics, everything at different energy scale that we're interested in. But as we all know, this is not the situation. And we're competing at the moment in a landscape of different models. And this is a slightly different landscape as compared to the standard string theory landscape. This is a landscape of different effective field theories that we are, as a community, coming up with to describing various types of phenomenon. And in trying to segregate between these different types of models and understanding which one is a better representation of nature, we're trying to put different tests in the game and having more and more experiments and observations to look for signatures. And just as an example, not that this is going to be particularly relevant for this talk, but just as an example, within the context of dark energy, effective field theories of dark energies, these are the different type of models that had been proposed in the literature, and even that is not quite exhaustive. That was about 14 years ago when I gave a summer school and trying to understand the different ways people have been at the time exploring various models of what dark energy could be. So that was 14 years ago, and more recently, I tried to go back and see if we could extend this picture to the models that had since then been developed. And there's been a huge plethora of even more models that are coming up in the literature, and they're interconnected. And each one of those models have some virtues, which each one of them has some signatures. Some of them are starting to be rolled out, while other models are starting to be populated in various different type of directions. So I'm not going to be talking at all about any specific bubble in this diagram and trying to advocate why this is the ultimate model for everything. Rather, within this context of a landscape of different models, I'll try to understand how we can navigate in that landscape and make progress and ultimately make contact with an ultimate high energy completion. So if we take a bottom-up approach, the first thing we like to do is to develop a low energy effective model to describe a particular phenomenon that we're interested in. For instance, dark energy. But you can do that for dark matter, you can do that for anything else that you may be interested in, and even for physics beyond the standard model. So this is a particular model, maybe one bubble in this diagram. And then once we set up on a particular model, we like to set up, before we even go and do some observational constraint, we want to set up the theoretical consistency of the model within itself. So just trying to understand whether the model is at all even classically stable, whether it is physical, whether it's even valid in the region where we like to use it for, whether it makes sense as a theory where we should be using for. And those are standard theoretical constraints that we are all used to imposing on our low energy effective field theory just by establishing the self-consistency of the model in the regime where it should be applicable. Now, if we believe that our model may have some chances of being theoretically viable, then it makes sense to try to come up with some signatures and see how it compares with the real world, and see in which region, for instance, of parameter space we may be converging into. So these are different examples. For example, this is for models of effective models of dark energy, or this for standard model, the FD of the standard model, so for physics beyond the standard model, or various type of paradigm that you may be interested in with various parameters that can be dialed in and out so as to accommodate for various observations. So in principle, we can continue this approach and refine where we are in parameter space in various models, and continue, and hopefully a specific region in parameter space, a particular model will stand out as being the best description for the world that we experience. So this is a definite valid approach, which we are all using, and it's a bottom-up approach where we develop models and then we compare and we establish some self-consistency test, and we converge towards hopefully a particular region. But what I'm interested in is trying to understand whether there's a way to complement this type of approach with something that will bridge with our ultimate high energy completion without relying on a specific high energy completion. So I don't want to start with a specific string theory compactification, for instance, and cascade my way down to particular models. I want to remain relatively agnostic on what the high energy completion may be, but still I would like to have some attempt of bridging between low energy as we observe it today and the potential existence of an ultimate high energy completion. And this is not as trivial as you may seem. It's not because you have a low energy model, which may seem to be completely consistent with itself. It is stable, it's classically stable, quantum mechanically perturbatively stable. It may seem completely consistent within itself. It may be completely consistent with all of the observations and experiments that we are familiar with. And yet for some of those models, we know that it will never be embeddable in a high energy completion. And you can have string theory, you can have another type of high energy completion with some given assumptions, but relatively generic. You can have another high energy completion that we haven't even come up with. And for some of the models, we know they will never be embeddable in a high energy completion. So this is in spirit similar to the landscape program, to the swampland conjecture, where we're trying to put some constraints in the phenomenology, in the theoretical approaches for theories at low energy, based on the assumption of a particular high energy completion. But the procedure I'll follow is not a conjectural approach following from different type of swampland conjectures. Rather, it's coming out from very specific assumptions on what we would like our high energy completion to enjoy, to satisfy. And those are the assumptions I would ultimately like my high energy completion to satisfy. I like the notion of unitarity in terms of probability making sense, a quantum mechanical sense. I want some notion of locality so that I can define physics locally and I'm not too sensitive to phenomena which are located a large distance away. I like to consider Poincaré to be a fundamental symmetry. I'll talk a little bit more about this. And I like to consider causality as being present, some notion of causality. And with that in mind, you can dial more or less some additional assumption. You can further ask for weak coupling or tree-level weak completion of your high energy completion, or you can ask for specific string theory compactification, for instance, or you can become less and less sensitive to assumption and relax some of your assumptions. But the basic assumptions that I would like to have in my high energy completion, without being too sensitive to some specificities of my energy completions, are those ones. And so this type of communication between the high energy behavior and the low energy effective field theory go under the name of the S-matrix bootstrap, or what I'll be considering is something complementary, which is the notion of positivity bounds, which allows to make some connection between the high energy and the low energy in ways that I can explain in a second. But first, I'd like to talk a little bit more about the notion of causality, and in particular within the context of Lorentz invariance. So everything I'll be talking about today is with the assumption that Lorentz invariance is a fundamental symmetry. No matter what happens in the high energy UV, I will assume that Lorentz invariance is preserved. The reason, and there's many reasons why I believe that Lorentz invariance is fundamental, although we can disagree with that. There are various tests of the equivalent, of Lorentz invariance, particular from gamma ray burst and other type of cosmic rays, which puts very strong constraints on any modification of Lorentz invariance, in particular in modification of the dispersion relation for photons at extremely high energy. And that tells us that the scale at which this Lorentz invariance has to be broken, if it is broken, is extremely high, sometimes higher than the Planck scale itself. And so from my perspective, it does make sense to imagine that Lorentz invariance is preserved all the way up to the ultimate completion of quantum gravity. And this is not to say that the EFT that we will be considering may be on a background that spontaneously breaks Lorentz invariance. For instance, I can consider an EFT for cosmology, or I can consider an EFT about a black hole, which will spontaneously break Poincaré invariance, for instance. So I can have an EFT which is on a background itself, but this background is a spontaneous breaking of Lorentz invariance, and I'll consider still that ultimately at high energy, I should remain insensitive to whatever spontaneous breaking of Lorentz invariance I had, and Lorentz invariance should be preserved. So with that key assumption in mind, what I try to do is look at the statement of causality and positivity in standard low energy effective field theories. So how some of those assumptions of causality and unitarity and locality at high energy cascade down to some bounds that we can impose on ourselves for the low energy effective field theory. And I will do that without gravity to start with. I will see how it puts us in some regions of this landscape of models. Again, this is not the string theory landscape, it's just the landscape of different type of effective field theories that people are considering. And then I'll introduce the subtleties that come in when we start dealing with gravity, and I'll try to understand how I can use causality constraints to constrain effective field theories relevant for gravity. So the first thing in all of those things and all of these statements is the notion of causality, and this is why I wanted to make very explicit the fact that I'm going to rely on Lorentz invariance as a fundamental symmetry. Otherwise, causality cannot be relaxed. You preserve causality can be relaxed. And if you have Lorentz invariance, generically, we all learn at some point in our life that you can have a low frequency phase velocity to be superluminal so long as the group velocity itself is luminal or subluminal. This is typically what we learn. And we learn that if the group velocity is superluminal, then we can have a violation of causality if you have Lorentz invariance. The reason for that is if I consider this is a space-time diagram, so I have time in the vertical direction, space in the horizontal direction. If I have an event at A, which has a time smaller than what happens at B, if I have superluminality, the point A, the event at A, can affect the event at B, which is outside the light cone of A. But now if you have Lorentz invariance, if you consider it to be a fundamental symmetry, then you can boost yourself, and boosted observers are equivalent. I can boost myself to a different notion of space and time, which would move at a given speed with respect to us. And for that boosted observer, the event B is happening at a time prior to the event A. And so for this boosted observer, the future can affect your past. And this is typically related to the notion of causality if your future can start affecting the past. So that's at a zeroth order level why any notion of superluminal group velocity, even though it could be tiny, in principle, if you have the smallest amount of that, you can perform a boosted transformation and end up in a situation which would be acausal. However, technically, the statement that group velocity should be subluminal to preserve causality is not entirely correct. It's correct sometimes, but not always. Actually, causality demands not that the group velocity be subluminal, but rather that the speed of propagation of information be itself luminal. And the speed of propagation of information is actually the front velocity or the infinite frequency limit of the phase velocity. So if I had a diagram depicted in here, there is the frequency of the modes I'm interested in and the phase velocity as a function of this frequency. So this is characterized by the dispersion relation. What we need to have for causality to happen is that the front velocity be luminal, but in principle, the phase velocity at low energy and the group velocity at low energy could be superluminal without necessarily imposing some violation of causality. And this is not only true theoretically, it does happen in nature. In the real world, the group velocity is sometimes measured to be superluminal, and of course, there's no violation of causality. There's many different experiments that have done it. This is just an example from this paper with using optical fibers, which they show that the group velocity in that fiber optic can be faster than the speed of light in the vacuum, so they can be superluminal. However, the front velocity, which they call him the information, the signal velocity, itself is luminal and does not exceed the speed of light. So this superluminality of group velocity can happen in systems that effectively break some level of unitarity at the level of the subsystem itself, not as a whole, but just at the level of the subsystem, because they are exhibiting gain, so they are taking energy from the overlying system, and so the imaginary part of the diffracting index in this case can be negative. These are not situations we'll be considering. We want to remain in situation where we preserve unitarity of the system when being interested in. And so typically, when you preserve unitarity, when we have the imaginary part of the refractive index being positive, we'll need to have that the low energy group velocity, and in our case, it will be the same as the low energy phase velocity, has to be subliminal, liminal or subliminal. We have the low frequency phase and group velocity being the same if we're considering massless waves, for instance. I'm not going to be too concerned about small IR corrections of those. So typically, we need to have a statement about causality which manifests itself at low energy, even though technically the statement of causality is a statement about the infinite frequency limit of the phase velocity, so something in the UV. So already at the level of causality, you see that there seems to be a mixing between what technically the notion of causality tells us, which is something in the deep UV, and how we want to use it within the context of low energy effective field theory, where we only have access to to low frequency velocities. And then in our everyday life, we are able to determine some statement of causality using low frequency modes. So just to give you an example of why we can do that, we can simply imagine what happens when we shine light through a prism, for instance, through glass or through some water. As we do so, some of the frequencies of light, those for which the wavelength of light is similar to the interatomic distance in the medium, are going to be affected by the presence of the medium, and interactions with the medium is going to slow light down in such a way that you're going to have lower frequency light traveling through that medium slower and coming out slightly in a different slightly angle than higher frequency light. And it is always the case, we can prove that in this situation, it's always the case that the speed decreases as you go to lower and lower frequencies. There's actually a theorem, and this is why we typically state that we need to have the low frequency phase group velocity here, the same for me, being subliminal, so that as you increase to higher frequency, the speed will increase and you can get to liminal at higher frequencies. So this has been well known for quite some time. It goes under the name of the Kramer-Kronig dispersion relations. And what we'll be interested in will be some relation at the level of scattering amplitude, but already at the level of the refractive index, the situation is very similar. So I can consider a dilute gas of atom, for instance, water or glass, and determine the refractive index within that medium. And the phase velocity in that medium will be related to the real part of the refractive index. Now, the imaginary part of the refractive index itself is related to the interconnection of light through the medium. And unitarity tells us that the imaginary part of this refractive index has to be positive for any frequency. And using some statement of causality and analyticity, this is kind of a textbook formula, you can relate the real part of the low frequency refractive index with a Cauchy integration formula over the imaginary part of the refractive index. This is just a Cauchy integration formula where you relate what's happening along the real axis to the whole imaginary part of the refractive index. And so unitarity telling us that this imaginary part has to be positive directly tells us that the phase velocity at infinite frequency would always have to be larger than the phase velocity at lower frequency. It always has to be monotonic in one way if you preserve unitarity. And so if you want the phase velocity at infinite frequency to be luminal, you need to have the phase velocity at lower frequency to be necessarily subluminal to preserve your conditions of analyticity, which are related to those of causality. So this is why typically we're considering that even though the statement of causality is a statement at infinite high frequency, we can relate that back to some statement at low energy, which are relevant for our everyday experiments, and telling us that the speed at low frequency has to be subluminal to preserve causality. So now we can make those statements a little bit more precise at the level of the scattering amplitude. And I'll repeat the same argument. I won't do anything other than just this type of experiment, but just re-express it a little bit more concretely at the level of the scattering amplitude. So let me imagine that I have a low energy effective field theory, which includes some fields that I want to use to describe some phenomenon in nature. It can be light, or it can be some dark energy field, or dark matter, or the Higgs boson, whatever you'd be interested in. And what we like to understand is what happens when we scatter those fields within themselves or with other fields. I can define a scattering amplitude between scattering amplitude for the process, the probability of the outcome when we scatter those fields. I'll be considering a 2-to-2 scattering amplitude, and I'll be working in Mendelssohn variable where I have the center of mass energy square and the momentum transfer related to the scattering angle in this process. Now, if I consider this scattering amplitude in a complex energy square plane, I'll have some poles and branch cuts in the real axis related to the ability of having some local transfer of particles, and some loops are coming from the branch cut. So looking at this diagram more precisely, if I have a low energy effective field theory, there will be a regime where I can compute this scattering using my low energy effective field theory and trust the result. So there will be a regime of validity of my low energy effective field theory where I can directly compute what happens with the tools that I have. And then in typical theories, there will come a point where this effective field theory breaks down, when new high energy physics has to be included in for us to being able to appropriately describe what is going on. And I don't know what this new physics is, and I don't particularly want to know either. I want to remain quite agnostic on what this new physics is. There may be an infinite number of layers of physics that come in, and that needs to be folded in all the way to a ultimate UV completion of everything, possibly including gravity. So I certainly cannot use my low energy effective field theory to compute the outcome of scattering processes in this region. I certainly cannot do that, but the amplitude itself still exists. And it's still reasonable to expect that the amplitude itself will satisfy some rules, for instance, of unitarity, which makes sense even though we're using them at very high energy scales in the Lorentz invariant sense. So while I cannot use my low energy effective field theory in this sense, I can still consider this amplitude being valid or being computable through other means all the way up to very high energy. Now, the notion of causality, which manifests itself through some statement of analyticity, is precisely, as we've seen before, what allows us to make the connection between the UV physics and the low energy effective field theory. This is exactly what we've seen in the case of light shining through glass or through the dispersion relation. The statement of causality at the level of the scattering amplitude in a complex energy square plane is the statement that the scattering amplitude should be an analytic function, and therefore I can analytically continue what happens between the low energy, the amplitude, and what happens at high energy, or vice versa. By that, what I mean is that there shouldn't exist any poles or branch cuts in the imaginary plane of this structure. Otherwise, that would create some support outside the light cone for my retarded propagator, and that would correspond to a violation of causality. And so it is this notion of analyticity that allows me to connect the UV to the IR. And once I have this connection, then I can impose on myself the remainder of the assumptions that I wanted my high energy completion to enjoy. In particular, I like high energy to remain unitary, and that manifests itself through the optical theorem. So if I compute a scattering, 2 scattering amplitude, we know from the optical theorem that the imaginary part of this amplitude is related to the sum of all of the intermediary processes squared, and so has to be positive definite. So that tells me that the imaginary part of the amplitude along the branch cut, the right-hand side branch cut, has to be positive. And then using crossing symmetry, we can also relate that to the statement that the imaginary part of the amplitude on the left-hand side branch cut has to be positive. Now, if I further ask for causality, as I mentioned before, this is the key assumption that allows me to connect between high energy and low energy behavior. And just like it was the case when we did the same type of relation with the refractive index, we can use the statement of analyticity, which comes from causality, in relating what's going on at low energy with a contour integration, Cauchy contour integrals of a contour which goes up to arbitrarily high energy scales. So here's just a Cauchy integration formula if you remove the low energy poles. And then finally, the statement of locality, which first manifests itself under the Froissart bound, that tells us that we want the amplitude not to grow too fast as we go to infinity, tells us that those contour at infinity, the contour at large radius, we can send them to infinity, and the argument of the integral will go itself to 0, and so they will just decay away, and we are left with the contribution of the amplitude at low energy being related directly to the integration of the imaginary part of the amplitude along the branch cut, the left-hand side branch cut and the right-hand side branch cut, which themselves have to be positive. So the statement of unitarity at high energy, all the way up to my ultimate high energy completion, has to manifest itself in some statement of how the amplitude behaves at low energy. That's very similar to the statement we were saying before, that the phase velocity at low frequency has to be smaller than the phase velocity at high frequency. This is just telling us that as we go from high energy to low energy, we're just including more and more spectral density, if you want, which contribute positively to the overall amplitude, and therefore we need to have a result at low energy which is positive by itself, because we're summing up positive contributions. This seems to be relatively naive statements. Hopefully it seems quite natural. I don't know how natural this derivation is to everyone, but this seems to follow quite clearly, and the relation with causality seems to be quite straightforward, but it has some very strong implications for all sorts of effective field theories. And this is not something I'm working explicitly in the SMEFT, in the EFD of the standard model for physics beyond the standard model, but I just thought I'll bring it up to illustrate how powerful this type of constraints are, just in diagnosing in which region of parameter space we can expect physics beyond the standard model to lie in. So if you just consider, for instance, dimension 8 operators for the SMEFT, for the boson operators in the SMEFT, you have a huge number of different type of operators with associated Wilsonian coefficients. And you can expect in the future, this is just as an example in a two-dimensional phase space among these Wilsonian coefficients, to be within some region of parameter space, just from experimental ground. That's where you would expect it to be, where the origin is just having none of those operators there, so just the standard model. And in green is the region where you should lie in so as to satisfy those type of previous positivity bounds. Not just this one, but similar ones, which I haven't derived. So if you're outside this green region, if future experiments tells you with great confidence that you are, for instance, in this region here, which is in the blue region, but not the green region, then you know that there's something wrong with the assumptions that you impose on yourself at high energy. So that would tell us that low energy physics that we're encountering is not consistent with the assumption that high energy physics is unitary, causal, local, and Lorentz invariant. So these have quite high implications for all sorts of effective field theories. Now, in terms of connecting this with the notion of causality again and the notion of subliminal speeds, you can imagine doing the same thing for a much simpler case, which is the effective field theory of a scalar field at low energy. So let's just imagine I have a high energy theory, which includes both light fields and heavy modes. And I just want to integrate out the heavy modes and end up with a low energy effective field theory for my light modes, where I don't need to know too much what my heavy modes are doing. So for instance, at high energy, I have a light field phi and a heavy field h. And if I'm computing some scattering amplitude for my light field, there are some processes which involve some exchange of the heavy field. But if I'm working at low energy scales as compared to the mass of my heavy field, I don't really need to include this heavy field in the game. I can just integrate things out and obtain a low energy effective field theory just for my light field, where instead of having this exchange of intermediate massive particle H, I just have a contact term. This operator to leading order captures those type of interactions with the heavy field. Now, whether you are in the high energy or partial high energy approach or the low energy approach, in this specific example, you can compute the derivative of the amplitude with respect to this center of mass energy square, and you'll get in here two factors of this coupling constant. So you'll get something which is manifestly positive if you preserve unitarity, in this case, if the coefficient alpha is real. So this is a direct consequence of unitarity of your theory at that level, which then manifests itself at every level. So the consistency of a potential partial UV completion tells you consistency of those positivity bounds that need to be satisfied within the regime of validity of your energy effective field theory. And this is also what is connected to the statement of subliminality, sound speed or phase velocity at low frequencies. In this particular example, where you have a d phi to the 4 operator like that, you can see, for instance, that if you consider fluctuations on top of a background, which itself spontaneously breaks Lorentz invariance, it has a profile along a particular direction, but the theory fundamentally is Lorentz invariant. You will have on top of that background, you'll have the speed of your fluctuations, which are no longer luminal, but ensuring they are subliminal tells us that the coefficient alpha here also has to be real, which is related to unitarity at high energy. And you can see that the positive interactions of the field with the medium, which are capturing interactions also with the high energy field, tells us that the system has to be slowed down in a particular way. It cannot be excited so as to go faster than light in the vacuum. Okay, so, and I should have said, I'm working in units where the speed of light in the vacuum is 1. Sorry, I should have said that before, if it's confusing. Okay, so everything seems to make relative sense in a non-gravitational effective field theory. Now I'll try to understand what happens in a gravitational context. And there's various reasons why I'm interested in applying this in a gravitational context. Some of them, you may wonder why I'm just worried about Planck scale corrections in something which will have much larger corrections from maybe standard model effects or other type of things. But I'll motivate that through the weak gravity conjecture itself. And then in going to the gravitational setup, I like to make the bridge towards ultimately being able to apply those considerations for cosmology, even though I don't have the tools to do that at the moment, but that's ultimately where we want to go. And then applications of towards the FT of gravity, in particular the relevance of some operators and how they can get imprinted in the gravitational waveform during, for instance, black hole mergers or those type of situations. But let me start with the weak gravity conjecture, where really the Planck scale suppress effect coming from gravity are themselves extremely relevant. So I don't know if everybody's familiar with the weak gravity conjecture. Let me give you the very quick cartoon, very overly simplified version of the weak gravity conjecture. This is not going to make it justice to all the work that's been going on into that. But if we consider a U1 coupled to gravity, so you can imagine this to be electromagnetism, but really what people have in mind is more of a new sort of beyond the standard model U1, so not electromagnetism. And let's imagine that black holes are then charged with respect to this U1. And if you consider an extremal black hole, which is charged and has a charge equal to its mass in units of Planck scale with respect to this U1, as it evaporates, in order to avoid naked singularities, you need to ensure that it evaporates in such a way that the charge of the black hole decreases faster than the mass of the black hole. Otherwise, it will become a super extremal black hole and you'll end up with a naked singularity. But for the charge to be able to decrease at least as fast, if not faster than the mass of the black hole, you need something to carry away the charge of the black hole as the black hole evaporates. And so this is what led to the formulation of the weak gravity conjecture, which says that for every U1 beyond the standard model, there must be a massive charged particle with charged larger than the mass. So if you consider electromagnetism, the electron very easily satisfies this rule. Remember, we're talking about Planck scale masses here. So of course, the mass of the electron is such that its charge is in units of Planck scales is much, much larger than the mass of the electron. So that's easily satisfied. But for any other beyond the standard model U1, this type of conjecture has to be satisfied. Now, there's a slightly different twist on this weak gravity conjecture, which tells us that if we consider an effective field theory of gravity plus this U1, you won't just stop there. You'll have an infinite number of operators that will come in your effective field theory. And those operators that come in, that capture even higher energy effect, they will redress your notion of black hole mass and your notion of black hole charges, because they slightly modify the black hole, the charged black hole solution. And so accounting for those corrections, which are small, this W, I should have said, this W is the Weyl tensor. So it's related to the curvature correction. So this is where Planck scale corrections come in. But it leads to a new extremality condition, which is not just that the charge over the mass of a black hole is 1 units of Planck scale, it's 1 plus small corrections coming from the FT operator corrections. And then you see that if those operators come in such a way with Wilsonian coefficients, which are such that this is always positive definite, if this contribution is always positive, then as the black hole evaporates, the mass becomes smaller and the black hole itself satisfies more easily the sub-extremality condition. So that means a black hole can evaporate without leading to naked singularity and without needing to postulate a massive charged particle with charge larger than its mass, other than the black hole itself. The black hole itself satisfies the weak gravity conjecture from the outset. So people have been trying to prove the weak gravity conjecture like that. And this is where the connection with positivity bounds comes in and the connection with causality comes in. Because if you have an effective field theory and you can say that no matter what happens at high energy, the behavior of high energy physics has to manifest itself at low energy in such a way that these operators come in so that this coefficient is always positive definite, from those sorts of positivity bound, then you can prove the weak gravity conjecture. That would be a proof of the weak gravity conjecture. And people are very close to this proof. One thing that has been shown, though, is that if you want photons themselves to remain luminal or subluminal on curved backgrounds, you typically require this condition with those coefficients A and B to be positive definite to prevent superluminalities. So once again, everything seems to make sense in itself. If you could have positivity bounds proving that this statement is positive, you could prove the weak gravity conjecture, and it would seem to make sense with statements of causality or statements related to superluminalities. So all of this so far seems pretty good. The only caveat is in the presence of gravity, the statement of causality through analyticity and various type of other consideration manifests itself slightly differently through positivity bounds, which themselves manifest slightly differently through subliminalities. And so there's many different reasons why causality manifests itself differently in the presence of gravity, but the main reason is the slight breaking of analyticity due to the presence of the graviton exchange pole that occurs as soon as you let gravity be part of your game. So if we reinvestigate the positivity bounds that we had before we explore them without gravity, now let me introduce gravity, and let me even consider a scattering amplitude where I'm not interested in gravity per se. I'm just still scattering photons or electrons or whatever you'd be interested in. But as you do that, if gravity is dynamical, you can't prevent from also including a contribution which comes from a graviton exchange. And you're going to tell me, well, this graviton exchange is incredibly suppressed, which is absolutely true. It's suppressed by the Planck scale. So it leads to a pole in the amplitude itself. This is what we call the T-channel pole. So we have a presence of a pole for exchange of any massless particle. So the same is true for the photon. The residue of the pole is related to the spin of the particle. So for the photon itself, the residue will grow like S. And so this is something we can subtract out easily. That wouldn't contribute in the second derivative of the amplitude with respect to S. But for the graviton itself, that's precisely when it seems to saturate the Froissart band, and therefore we can't remove this contribution from the amplitude when applying the positivity bounds. And so the presence of a graviton exchange, the presence of a massless spin-2 exchange that is present as soon as you let gravity play along within your effective field theories, even though it will be Planck suppressed, is precisely what compromises the applicability, the strict applicability of those positivity bounds. So you may ask yourself whether you can still impose that the coefficient of the remainder by itself is positive. And the answer is, strictly speaking, no. And actually, we know in nature processes where graviton does spoil the remainder of the amplitude in such a way that this coefficient C ends up being negative, always negative. This is, for instance, the case if you compute, among other things, but for instance, if you compute graviton-photon scattering, including loops from the standard model. So I call it haha, because that's gravity making fun of us in return. So if I compute a graviton-photon exchange, including loops from standard model particles, so for instance, the electron, the W, and the Z bosons, and other type of loops, the contribution to this amplitude at low energy will be dominated by the lightest charged particle, which in the case of electromagnetism, if I consider the photon here, it will be the electron. So now if I compute the remainder of the amplitude, so the pole subtracted amplitude, this coefficient here, in this case, can always be made negative. I can always find a choice of photon polarization for which I end up with a negative definite result here, where this coefficient here is related to the charge and mass of the electron. And so this can be quite negative. It's always dominated by the lightest massive particle. So with gravity, we need to learn the fact that, strictly speaking, the positivity bounds are not applicable, and we'll have to have a small amount of negativity. And so this small amount of negativity is directly related to how we accommodate for causality within low energy effective field theories, how we have some notion of subliminalities or subliminalities are low energies, and is directly related for attempts to proving the weak gravity conjecture. So just to recap, in a non-gravitational effective field theory, we can have, through ground insight of unitarity and causality, the derivation of positivity bounds, which tells us that some qualities of the amplitude, some properties of the amplitude part of it have to be positive, and that translates back into some statement of subliminality, which seems to be related to causality. In gravitational effective field theory, it's a little bit more murky, and we have to learn to live with instead approximate positivity bounds, where technically speaking, those coefficients are not positive definite. You can allow yourself a little bit, a slight level of negativity, which is of course carried by the Planck scale. So when you send the Planck scale to infinity and you decouple gravity out of the game, then you recover a strict positivity bound. But when gravity is in the game, and when you're interested in such effect, then you need to account for the fact you have a small level of negativity. And this small level of negativity is also related to a small level of what you typically qualify as superluminality, and yet this should be consistent with causality. So very shortly, I'm going to try to understand how, if we can allow for superluminalities in low-energy gravitational effective field theories, how causality manifests itself. How can we diagnose the statement of causality? But before that, I just want to say that this also has implication for the weak gravity conjecture. If positivity bounds were allowing ourselves to prove that this coefficient was positive, we could have proven the weak gravity conjecture. Not me, this is some other people in the literature very close to proving that statement. Unfortunately, at the moment, the best we can do is to have an approximate positivity, and so an approximate weak gravity conjecture, which is not sufficient to really allow you to prove that the naked singularity are always never occurring in nature, for instance, from the evaporation of extremal black holes. Okay, so I have a few more minutes for the last part, which I reassure is going to be a bit quicker. Well, I'll try to understand how the statement of causality can manifest itself in low-energy gravitational effective field theories, having in mind that it's not as simple as simply saying that everything has to be subliminal. So, of course, if I knew everything, I would know, if I had an ultimate high-energy completion of quantum gravity and everything that goes beyond it, I could, principle, not me, but someone else clever than me, could cascade down and derive the low energy effective field theory, able to describing everything that we want at low energy. But we don't have that. And so all we can do at the moment is, from a bottom-up approach, content ourselves with parameterizing a lack of knowledge through operators and Wilsonian coefficients I haven't written down in a low energy effective field theory. And depending whether we have a notion that it should be completed at the loop level or completed have a tree level high energy completion, the scales involved will be slightly different, but otherwise we'll have an infinite number of operators that would come in. I just wrote a few in there. And once again, I like to understand how do I diagnose which among those effective field theories makes sense in terms of being ultimately embeddable in a causal high energy completion. How does causality manifest itself at low energy, knowing that just stating the absence of superluminality is not the right criteria, because in gravitational effective field theory, we can allow ourselves for a minor level of superluminality and still be consistent with causality. These are things that happen in nature. So I'm just going to be very cartoon-like in here, because I don't want to invade you with lots of equations. So it's just going to be a series of cartoons to show you the picture. But let's imagine, just if you remember the picture where we had light shining through glass earlier, I want to do the same thing with gravity. So instead of the glass, my medium that spontaneously breaks Lorentz invariance. For instance, I can take a black hole. You can take PP waves. You can do whatever you want. But just for concreteness here, I'll take one black hole. And rather than shining light through it, I'm going to shine a gravitational wave through it. This is just because I'm interested in the FT of gravity. So the analog of line shining through a prism here will be gravitational wave being scattered in the vicinity of a black hole. So this would be the trajectory followed by light modes. for instance, light itself, if you didn't have any other corrections, or followed by high frequency gravitational waves. Very, very high frequencies. This is a notion of luminality, and high frequency mode should always ultimately go back to precise luminality. So this is what I'll consider being my null geodesic on that background. But now through interactions with other fields, low frequency gravitational waves can feel the geometry about the trajectory. And so on this curved background, the low frequency gravitational waves can follow a slightly different trajectory and effectively look like they're traveling at a different speed. They will follow a slightly different type of geodesic, as if you had a different speed. Effectively, we can characterize that as a speed of propagation of the light frequency gravitational waves, the small frequency gravitational wave, which is almost luminal, the corrections that come in from the curvature of the background, the curvature of the black hole, because this is what is capturing the breaking of Lorentz invariance, the fact that we are having stuff present in there. And of course, it's Planck scale suppressed and related to the mass of the other particles, the other interactions. So this is the scale at which the other operators come in. So that is what happens at low frequency. At high frequency, we'll have more and more corrections, which are going to resum such that ultimately, as you go to high frequency, you'll end up being all of those corrections canceling out and the speed being exactly luminal. But you can go from a sub or superluminal speed at low frequency to something which is exactly luminal at high frequency. Now, the typical approach that myself had been following before was to try to make sense of these low energy effective field theories by constraining the operators that I have in my EFT such that about any situation I always have strict subliminality. But as I mentioned, this is not the right procedure, because in different situations, what you mean by sub or superluminality may be different. And because a small level of superluminality, which is Planck scale suppressed, is not always in tension with causality. And so should not be used as a way to disregard some operators in the low energy effective field theory without doing a little bit more work. So to be a little bit more concrete on how we can see that a small level of superluminality with this, such that the whole thing is positive, may still be consistent with causality, I can compare the time delay, the phase shift between the null geodesic followed by high frequency gravitational waves, or followed by massless light, for instance, and that followed by my gravitational waves at low frequency. And so I have a time delay between the two trajectories, which can parameterize by delta L, for instance. But at the same time, as I proceed to this experiment or thought experiment, I need to make sure that if I'm going to use my low energy effective field theory with those operators to compute what happens, I need to remain within the regime of validity of my low energy effective field theory. And so I cannot be too close to the black hole itself, and I cannot send too high frequency modes to probe this geometry. Otherwise, I'm not going to be any longer in the regime of validity of my low energy effective field theory, and I cannot trust this result in the end. So what I have to do in a situation like that, where now this is just poor drawing, but this is my way of trying to show that we have waves of particular frequency, but such a signal would typically be too high frequency to be trusted too close to the black hole. So there's combinations between the frequency, this scale invariant combination between the frequency and the curvature of the space-time, which have to remain within the regime of validity of my low energy effective field theory. And so I have two choices to remain within the regime of validity of my low energy effective field theory. Either reduce the frequency of the signal that I sent in, and that corresponds to fuzzing it around, and ultimately the time delay or advance that I get from scattering those gravitational waves is not going to be resolvable. It's going to be smaller than the wavelength. I increase the wavelength of the signal so much that the support that I seem to be having is ending up smaller than the wavelength of the mode that I'm using to probe this geometry. and therefore there's no notion to which I'm measuring any support inside or outside the light cone of one mode with respect to another one. Or other than decreasing the frequency, what I can do is keep the frequency the same, but try to remain as far as possible as the black hole, so as to remain within the regime of validity of the EFT, so that the curvature is not too strong. But when we do that, the effect, the support outside the light cone, the time delay between the two signals is also going to be reduced because we have less curvature to carry it. We're closer to flat space-time. And then this support will also be smaller than the wavelength of the mode that we are considering. And so in the gravitational context, when I'm trying to probe a geometry, when I'm looking for the effect of loops of heavy modes, this is something we can prove in generality, it will always be the case that you always end up, even though you have the impression that you're in a superluminal region, the level of superluminality that you end up with is never resolvable. You can never end up with a support outside the light cone or a time advance that will be resolvable while remaining within the regime of validity of your EFT. And this is very different than what happens in the non-gravitational setup. In the non-gravitational setup, you can have some stuff that spontaneously breaks Lorentz invariance being present there. It doesn't back-react on the geometry, so you can accumulate it. And even though you start with an infinitesimal amount of superluminality, you can stack this stuff for an infinite region and end up with a macroscopic support outside the light cone, something which is measurable. With gravity, you can't stack things at will. You always end up with having a back reaction on the space-time, which leads to some curvature, which then leads to some region in which the EFT is no longer valid if you're trying to stack too many things around the same place, or even over a long distance in space and time. And so that's the key difference between gravity and the absence of gravity. And for a low energy effective field theory in a gravitational context, if you consider this EFT arising from integrating out loops of massive lower spin modes, you can prove that even though you have the impression that you have some level of superluminality sometimes, it will never be resolvable. The amount is always sufficiently suppressed that you have no tension with causality. So that's in the context of loop integration from heavy mode physics. And you can ask yourself the same question when you integrating out tree level from instead higher spin. So if you want to have corrections to the EFT of gravity from those operators at tree level, you have to integrate higher spin. And because it is tree level, those operators are enhanced by a Planck scale as compared to what you had when you had an EFT of loops, integrating out loops, because they are loop effects. So in principle, in an EFT, when you integrate out tree level of higher spin, the operators in your EFT are enhanced. And in that case, you can add up, have operators with Wilsonian coefficients which are larger in magnitude. And you can ask yourself the same question. If you start scattering gravitational waves in the vicinity of a black hole in this EFT of gravity with a tree level high energy completion in mind, what you see is that typically you can end up with a time advance outside the light cone, which even though is in principle small compared to the wavelength, is also enhanced by the fact that you're no longer with a loop suppression, you are with a tree kind of enhancement. So you have an additional enhancement of the effect, which can turn out having a time advance which is resolvable if the coefficient of the Riemann cube in this case is negative, has a specific sign. And so what you can show is that for a tree level high energy completion of gravity, for causality to be preserved, you will need the coefficient C here to be positive or zero. For a tree level high energy completion, causality would be violated if the coefficient of the Riemann cube was negative. And it has happened in any string theory realization of this EFT. Either the coefficient C is zero or it is positive, which is consistent with those derivations. So this is an example where, once again, if you put yourself additional insight on how you want your high energy completion to manifest itself, if you want weak coupling, or if you want further tree-level weak coupling, then you'll have more and more constraints on your low energy effective field theory. If you remain agnostic on the precise high energy completion other than those assumptions, then in principle, you can have any type of EFT operator in here, and that could still be consistent with causality. Okay, so I'll stop here as I'm running out of time. And I try to motivate it how one can use theoretical constraints which are not just embedded within the low energy effective field theory, like stability or perturbative unitarity, but some which are non-perturbatively connected with high energy completions, unitarity and causality all the way up to the UV, and that allows us to have forging further information on how we like our low energy effective field theory to behave. So some bounds on our low energy effective field theory. Thank you.
Thanks a lot for the great seminar. So now I think we can open for questions. Please raise your hand and or unmute yourself. We are also receiving questions on YouTube if you are there. So I will start with the first question. In your just previous slide, you have swampland, but you have a question mark. What is this question
why do
mark?
I have that? Because I'm not entirely sure what to put it in this arrow. Yes, it's not I'm questioning the swampland. The level of assumption is not in this space. It's a different space of assumption.
Okay.
So it's not classified in this way where you have, for instance, those bounds, or where you have weak coupling or tree level weak completion. So at the moment, we would love to make a better contact with the swampland conjectures, but the connection hasn't really been made, and it's kind of not really living in the same space of assumption. So I don't really know where to put it. What is clear is if you want to connect with the swampland conjectures, the behavior of black holes is key in most of the swampland conjectures. And what we're doing at the moment, particularly with those positivity bounds, most of it is without the black holes. They're not key to our insight. When we're trying to connect with the weak gravity conjecture, that's where black hole solutions come in. But even in trying to make that, let me go back. Even when we're trying to prove whether this can be positive, this is proven in flat space-time. It's not really directly at the level of the black hole. And all of the positivity bounds and most of the S-matrix bootstrap program is relying on being able to define the scattering amplitude, which will be in flat space-time and with Minkowski as a key assumption. So the connection with the swampland conjecture and the landscape is still, is not clear.
This S-matrix bootstrap has only been applied to 10D, right? Right at the moment, right? It's not a 4D, right? It's.
I mean, you can read some of those bounds as matrix bootstrap program. We're bootstrapping the high energy to the low energy, right? I think it depends if you want to consider more assumption on conformal UV completion as well.
Okay, because for 10D, the problem is more constrained, right? You have then 4D, you have more, maybe more when you use this S-matrix bootstrap approach.
That's right. If you have conformal invariance, then that's a whole new set of symmetry that we're not imposing in here. Yeah.
Thanks. So there is a question by Dimitri. Is Dimitri?
Yeah, thanks, Claudia, for a very nice review. So you mentioned this proof of weak gravity conjectures that I mean, people are really close, but it seemed to me that this is kind of model dependent, or maybe I didn't understand, because you were showing some particular set of operators some particular
No,
coefficients.
those operators are the leading operator. They're completely model independent. Yeah, so those operators are the leading operators. There's an infinite number of them that can come in. Can you see my mouse here?
Yes, I can.
Yeah, so there's an infinite number of one that will come in and it will contribute to higher order terms there. But all you need to care about are the leading order ones, are those ones. And I'm not saying where those ones come from. It doesn't matter what the high energy physics that led to those operators is. You don't need to care about that. Or at this level, if you want to apply positivity bounds, it tells you whatever the high energy completion is, so long as it's unitary. If it had worked out, it could have tell you that if you didn't have this T-channel pole, that this coefficient here has to be positive, and therefore you can prove the weak gravity conjecture in this way. This is completely model independent. You're not, these operators, they are the only one present at that order up to field wave definition. You can reabsorb it. There's no real physics in this field wave definition. Because they are relatively low dimension operators, there's not many of them. There's an infinite number of one you will need to include, but those are going to lead to subleading corrections in here. But what matters is really what happens in those leading corrections when you decreases them very close to the extremality condition.
Okay, I see. My other question is related to, so when you explain how the gravitational theories are different when you derive the positivity bounds, and you said that we should leave with a little bit of negativity, I didn't understand exactly why there is negativity there. So first, you mentioned that there is a contribution of the graviton in this scattering, right?
That's right.
And that contribution gives something negative in this relation.
Oh no, the sign here is not. I mean, it's fixed, but that's not really what is relevant. It's not the sign that matters. It's the fact that you have a pole here.
Okay.
It's not strictly analytic where you need it to be analytic. So you can't just take the second derivative of the amplitude with respect to S and apply it at its error. You'll get garbage. You can't do anything.
All right.
So through various type of considerations, you can consider that this is just something related to quantum gravity, and you'll have higher order modes, higher spin contributing to resolving this T-channel pole through a radio behavior, and that is just related to lighter field physics. So this is Planck scale surprise, whereas this is goes like you'd expect it to go like the mass of the lighter field before the onset of the higher spin tower. So you could think, well, maybe this should still remain positive because it's not so sensitive to the ultimate completion of quantum gravity. You could have the onset of a higher spin tower that contributes to the regularization of this pole and separate out the two. And you could have thought, well, this should mainly be the main contribution to this coefficient is from positive dispersion relation from loops of intermediate modes that will be positive. But that would be a very good argument. But the reality is, in the example that we look at, it doesn't happen like that. And this coefficient ends up being negative. So this, we can compute explicitly the contribution to the graviton-photon exchange amplitude and the coefficient of those S-squared term. We see that we can always find some scattering processes where it's not like this is positive and has a small irrelevant Planck scale suppression. It is simply negative. So you can't, and you shouldn't expect it to be positive. You can't apply the positivity bounds because this term violates it. But you see that it's not just your inability to apply the bound. This nature does give you realizations where this is actually negative. So you can't disregard that.
So and this gives, well, an example of superliminality being broken, violated, but not causality. I mean, we can still. Okay.
Exactly. So this is exactly related to a phenomenon that Rham and Hassel has shown some 40 years ago, that if you're in a curved background, for instance, on a black hole, around a black hole, and if you look at the loops of electrons, which are exactly related to those, the effect of loop of electrons on this curved background, they will give you the impression that photons are superluminal on that background. You get a speed which would seem to be greater than 1. However, for all intents and purposes, anything physical that you can get out of this small level of superluminality is not leading you to any resolvable violation of causality, and it's not even that you have microcausalities. You can't even have a resolvable support outside the light cone. The level of superluminality is so small. If you want to remain within this EFT, it will never be resolvable. So causality is preserved, even though technically speaking, you have some mild level of superluminality.
Okay, thank you.
So there is a question by Igor on the chat. He mentioned, how about the equivalence principle and the superluminal propagation? What is the violation, or?
No, it's non-resolvable. So it's not something you will measure. Yeah.
Okay. So another one by him, is the cosmic censorship conjecture a consequence of weak gravity?
So they are related, I guess. It's part of it, right? But that's just one potential naked singularity. So the weak gravity conjecture is for charged black holes, and you would like, yes, to prove that in this context you can never evaporate to a naked singularity that will violate the cosmic censorship. But that's one context. The cosmic censorship is much grander than that in many different other type of contexts. And it's very much in the dynamical evaporation of that black hole. So if you satisfy the weak gravity conjecture, it doesn't mean that out of the blue you can't spontaneously produce a naked singularity super extremal black hole. I think it does prevent you from doing that necessarily.
Okay, I think there is Giorgio. Please, if you want to unmute yourself.
Hi, thanks for a great talk. Sort of, to me at least, maybe the weakest of the assumptions that you made is about unitarity, because and everything, because unitarity, I mean, the black hole information puzzle, it's at least a possibility that unitarity is broken. And in non-relativistic quantum mechanics, it's possible. I mean, obviously probabilities goes to 1. Obviously, observables are not complex numbers. But within at least, until you do second quantization, you can just build a density matrix and basically say, states, you could have loss of coherence and you could go spontaneously change from state to state, and that breaks unitarity. And open quantum systems, this is related to horizons and everything. I'm just wondering if there is a way to include this in effective effective. I understand in the mathematics that you are using, I understand that unitarity is kind of unavoidable if you don't want to use to get absurd results, but physically it might well be broken. And maybe
so it's interesting because different people have different perspective, and people are typically happier to break locality or break even causality and get micro causalities so as to preserve unitarity. But I'm going to respect every point of view.
Well, I mean, just
let me just say, in terms of what you, I think, concretely asking is, can we use this approach to parameterize a potential breaking of unitarity at high scale and see how those relations are violated, and you can do that. Yeah. So here I'm asking for this quantity to be positive. I can allow it to be slightly negative, carried by some scale, which is the scale at which you may expect unitarity to get broken, and you can carry that through.
Okay. But does this mean that you get ridiculous results, like, you know, complex probabilities and stuff like that when you do that?
That is at the level of the formalism, right? I would say you need to tell us how you would like to make sense of this breaking of unitarity. And so I would say if this is through embedding in a bigger framework, because you're not dealing with an open system, you're dealing with an open system, I would say you should apply those rules to the grounded system, and then that's fine. If it's something slightly different, I can't tell you what you would get without. You need to tell me how you make sense of this breaking of unitarity, because I don't know how to make sense of it in the first place, right? I don't even know if I'm allowed to talk about this scattering amplitude in the first place if you tell me it's going to be violating unitarity at some point.
Thanks.
Okay, thank you. There is a question by Fabio. Please, Fabio, go on.
Thank you, Thiago, for the word. Claudia, nice presentation. I am using two notebooks. One is with the audio good and the other with the video one. Look, in some moment you made a relationship between the charge and the mass of the extreme black hole, right? Could you show again this slide? Yes. I would like to hear a comment from you if you have considered the situation in which the charge is decoupled from the mass, because this happens in some cases in some investigations.
So in which sense? You mean that the extremality condition is not a condition on the ratio between the charge and the mass?
Yeah. Or this is the only scenario that you achieve?
So I mean, I can have black holes with charges which are very different, right? Which are much which have no charge at all, and that's fine. It's only when I get very close to the black hole being extremal that I'm at the edge of the cliff, and so that's why I'm interested in that relation very close to the extremality condition. But are you trying to get very close to a naked singularity without playing with the charge ratio to the mass?
Okay, it's because when you compare the charge with the mass, in some moments you are saying that they are coupled, right?
No, they're not strictly speaking. No, this is just the point where the two horizons will collide, and so I'm looking very close to this to black holes which have a specific relation between their charge and the mass. But of course, in this theory, you can have black holes of loads of different charges. Most of them would be, you expect most black holes to be chargeless, of course, because as soon as it acquires a small charge, then it will go away. But here we're just looking very close to the extremality condition, because that's where we're the closest from the naked singularity.
Right. Thank you for the explanation and the good seminar.
Thanks.
Okay, so I think in the last that is a comment on the chat, a comment or a question, but I'm not. What if unitarity is replaced by isometry? I don't know if maybe you can.
Yeah. Do you want to elaborate? I'm not entirely sure.
Yeah, I'm also. Okay, so.
Yeah, I'm not entirely sure actually what you mean by that. But you can send me an email if you have, or if you, are you around always?
Okay, I think he's Yeah. Okay, so I think I have one last short question. When you put the constraints in the matrix, you put the causality. It's almost how you differentiate micro causality and macro causality in these constraints. It's
yeah. So that's a very good question. In reality, that's an excellent question. It's probably not a short question. It's a short question, a long answer that I can't even answer so far. So we're trading the notion of causality with that of analyticity. And I haven't gone through that too much, but this is technically that you can prove at the level of non-gravitational effective field theory, just like you can prove that the retarded propagator, for it not to have support outside the light cone or not to have support in the future, you need to have it being analytic in some part of the complex plane. And so this is a strict statement of causality. You can relax that a little bit by having some notion of microcausality. But here, actually, it's even, I would say, maybe slightly weaker, that what we're asking is analyticity. And everything is traded for analyticity. Now, that connection between causality and analyticity, even in the gravitational setup, is not precisely well understood. So it's an additional layer of assumption, if you want, on that.
Okay, so thanks again, Claudia, for the great seminar, and thanks everybody for participating, and see you next week with more seminars. Okay.
Next week we continue regular time.
Okay.
Thank you, Claudia.
Bye.
Thank
Bye-bye.
you, Claudia.
Bye bye. Bye bye, pessoal. All the best.
Thank you.